In today's tutorial, we're going to have an introduction to triple integrals, how to set them up, how to evaluate them, and so on. Now, we already know a little bit about double integrals, and when I was teaching you that in lectures, the idea was to sketch the region. Now, if we go up one dimension to three-dimensional regions and integration, it gets even more challenging. So we'll start off pretty simple, but there is one problem that I'd like to do if we have time, and that's the intersection of the cylinders. Has anyone done that question? Okay, that's a reasonably challenging question. Okay. Okay. All right. So I'm just going to start off with this one here. We're given the following repeated triple integral. We're asked to evaluate it and to interpret it as our answer as a volume. Okay, so let's just work our way through that, and I'll explain as we go. So I'm going to let I be the value of this triple integral. Okay. Now, the first thing we want to do is evaluate it and then interpret the answer. Well, actually, I think I'm going to do it the other way around. I'm going to interpret I as a volume, and then I'll work out the whatever I is. Okay. So let's have a look at our repeated integral. The z is between 0 and 1 minus x minus y. Okay? Now that's two surfaces. This top one's going to be a plane, and the bottom one's going to be a plane, so just the xy coordinate plane. Y will be between this function of x, just the 0 function, and this function of x. This is just going to be a straight line. And then x is going to be between two parallel lines. X is going to be between 0 and 1. So I'm actually going to sketch the region in first. So, okay, so here are my axes. Now, x is between 0 and 1, so let's just, I don't know, mark the line 0, x equals 0, and the line x equals 1 here. Now, y is between 0 and 1 minus x. Now, if I sketch that in the xy plane, y equals, I'll get something like that. Now, what about the plane, the two planes that bound the z sort of point, variable? Well, the plane z equals 0 is just the xy plane, right? Now, the plane z equals 1 minus x minus y, well, that's a little bit trickier to draw. But if you compare this with this, right, basically this and this is just the same when y equals 0, right? You know that this plane has to cut the xy plane along this line. Okay? And you can actually go and work out the other cuts to the other coordinate planes. Now, when x and y are both 0, this is going to be 1. Now, if I combine that, I'm going to get something like this. Okay, so this would be the line when y, so go up here, set in, yes, if I set the y equal to 0 up here, I'll get 1 minus x. So this is going to be the line, something like z equals 1 minus x, something like that. And I can get the equation of the other line if I really want to. Now, this kind of solid, anybody know the name? Tetrahedron. Tetrahedron. So you can think of this solid as being bounded below by the xy plane, bounded on this side by this xz plane, on this side by this yz plane, and above by the plane z equals 1 minus x minus y. So let's call the solid, say, S. Above, it's bounded above by z equals this. Bounded below by this. And on the other sides, by the, I guess, the coordinate axes, right? The coordinate planes. So, what is I here? Let's interpret it as a volume. I is just the volume of that tetrahedron. Okay? So let's actually go through and work out the integral. It's set up nicely for us. We didn't really have to draw a picture, but it is important to, get some spatial awareness. Okay, so this is the same type of evaluation as you saw with other integrals. You just do the inside integral first. So I'm integrating everything with respect to z, then move on to the next integral, then move on to the next integral. So the inside integral, we're integrating 1 with respect to z. That'll give me z. When I plug in this and this, I'll get the following. Okay, so I integrate that, I'll get z, then I sub in my limits of integration, I'll get this. Okay, not too shabby. So now I want to just do the inside integral in my bottom line. So I want to hold all the x's constant and integrate with respect to y. So this is going to become y, this will become minus xy, and this will become minus a half y squared. So now I'm going to sub in my limits of integration. So I'm going to get, well, when I sub in y equals 0, all the terms are going to be 0. Okay? And now I can just clean this up with a little bit of algebra. I can factor these terms in this term. So I get down to something like this. So I've got a common factor of 1 minus x in both of these terms. So when I take out when I factorise, I'll get this. So now I can just simplify nicely. Okay, I can integrate 1 minus x all squared. Well, what's it going to be? Well, this power is going to go to a 3. And then all I need to do is touch up something around here maybe. So if I differentiate this, I'm not quite going to get this. I'm going to get minus 3 out the front. So to counteract that, I'm going to multiply by minus 1/3. Okay, so when I sub in 1, I'm going to get 0. When I sub in 0, I'm going to get 1. And the negative sign ensures that we have a positive answer. Okay, so you may look at that and go, well, hang on, Chris, I could have easily got that answer just by simple geometry. just by calculating the volume there. Yeah, you can. But that's not the point of this question. The point is to, first of all, get you drawing some nice pictures, interpreting the region of integration, and then finally just knocking the integral over. Questions? Who's? Okay. Is that how you did it? Yeah? All right. Good. So that's a fairly basic one. The nice thing was that the integral was set up for us. Okay. I'll do 117. Sketch the solid bounded by this cylinder, this plane, and this plane. We're asked to sketch it and then calculate the volume. Okay? So we've got a couple of different surfaces and regions and things going on here. Just remember, cylinder, plane, constant plane, non-constant plane. Okay, and in particular, this is a cylinder wrapped around, the z-axis, so it's a vertical cylinder. So let's have a look at that one. Now, have you guys done cylindrical coordinates yet in lectures? Yes? Okay, well, you could do this question using cylindricals. I'm not going to do it that way because this is like an introductory tutorial on these things. But see if you can do this one using cylindricals if you're familiar with them. Anyway, let's sketch the region first. So this is 117. All right. So I'm going to say our region is, say, omega. The solid bounded by this cylinder, this plane, constant plane, and this non-constant plane. Okay, let's draw the solid of interest. Well, here you've got this cylinder and this plane below. So I'm going to draw that in. Okay, let's say that's 1. And so think of this as the intersection of this cylinder with the plane z equals 1. Now, how do I account for this? Well, as x and y both get positive, this is going to decrease, right? So in the first quadrant, this is going to sort of be sloping down towards that first quadrant. So the way I'm going to represent that is something like this. And I'm going to join them up. Okay, it's not a perfect drawing. So think of this sort of slice slanting down towards the xy sort of the positive or non-negative xy sort of quadrant. Okay. Now when x and y are both 0, this is just 9, so you can sort of intersect it there. Okay, not a perfect picture, but not bad. Now, one important pieces of information with these kinds of problems is to look at the projection of the solid on the xy plane. Okay? So this is my solid, and this is sort of like the projection of the solid. What points in the xy plane does the solid lie above? Okay, well, that's kind of a reasonable sketch. Let's actually compute the triple integral. So we know the following. The volume of omega is just the triple integral over the solid itself of 1. Okay, so how are we going to describe my region omega in terms of x, y, and z in Cartesians? Well, I'm going to do this all in one step. What are the surfaces that bound z? Well, it's bounded below by the surface 1, the constant surface, and it's bounded above by this surface. Okay, so well, what about x and y? Well, let's draw the projection in the xy plane. So it's going to cut at 2 and 2. Now, if I want to, say, put this all in Cartesians, I know that x is going to be between, well, let's just draw a vertical line. So this is y equals minus root 4 minus x squared. That's the bottom half, and this is the top half. Okay? So if I wanted to put two functions that bound y, well, the top one would be root 4 minus x squared, and the bottom one would be minus root 4 minus x squared. dy. What about z? Who can give me the z? The x bounds. Well, let's just slide this around. If I slide this around, what am I going to be between? I'm going to be between minus 2 and 2. Okay? Now, just looking at that integral, it's not very nice. So what I'm going to do is do the inside integral first and then switch to polars. Okay? But the only reason I describe this is just so you have a good understanding of the sort of Cartesian setup. So let's do the inside integral first. I integrate z, 1 with respect to z. I'm going to get 9 minus 3x minus 2y minus 1. Okay, so when I take one away from the other, I'll get 8 minus 3x minus 2y to y dx. Okay, so now let's switch to polars. Okay, hopefully you can see that. Well, okay, we could have started with cylindrical coordinates, but we're going to have to switch to we want to switch to polars down here. So let's describe this region in terms of polars. What's it going to be? Well, r is going to be between 0 and 2, and what's theta going to be between? The angle. 0 and 2 pi, right. So this is going to be 8. So we replace x with r cos theta and y with r sine theta. And we replace this area element with r dr d theta. Okay? Now, don't forget about the r here. Lots of students forget it. So let's, again, do the inside integral first and then outside integral. So when I multiply through here, I'm going to get 8r. When I integrate that, I'm going to get 4r squared. Over here, I'm going to get 3r squared, so I'm going to get r cubed. And over here, I'm going to get 2r squared. When I integrate it, will be 2r cubed on 3. Okay, so all I need to do now is plug in my r's. So when I plug in r equals 0, everything's going to be 0, so that's not a problem. The first term is going to give me 16 minus 8 cosine theta. I'm going to get 16 on 3 sine theta. Okay, so now just those little bits with respect to theta. Okay, so I won't do that last one because I'm running out of space. But if you do those three integrals and sub in 2 pi and 0, you'll get 32 pi. Now, it is a volume, so I'm just going to write it 32 pi cubic units. Now, we did set this up in Cartesians. Hopefully you can see how you could have sort of eliminated a lot of this work just by using cylindricals. Now, you may not be too comfortable with cylindricals yet. Don't worry about it. I'm going to do a real simple example in cylindricals a bit later if we have time. Questions? Okay. 118. Find the volume common to two cylinders. One's wrapped around the z-axis, one's wrapped around the y-axis. This is a bit of a brain bender if you're not familiar with it. Okay? So let me just show you one that I've created earlier. Bit chunky. Okay? So you've got a vertical cylinder wrapped around the z-axis, and you've got a horizontal cylinder wrapped around the y-axis. And at least in this picture, I know it's a bit fuzzy, but you can see the curves of intersection between the two cylinders. Okay, so if you want to sort of shave it a bit, that's the solid. Okay? And the question is, how do you calculate the volume? We can do it a few ways. You can do it using double integrals, using triple integrals, using single integrals, and lots of symmetry. Okay, so I can't draw quite as good a picture as that, so that's why I've prepared it earlier. But let's go and have a look at how you solve this problem. Okay. So what I'm going to do is I'm going to cheat a bit. I'm just going to draw the two cylinders separately. So let's consider the volume of two intersecting cylinders. Okay, so we've got one wrapped around the z-axis, here A is some positive number, and one wrapped around the y-axis. Okay, so I'm just going to draw them separately and then hopefully you can visualize. Okay, that's the vertical one. And the horizontal one is going to look something like this. Okay, again, not perfect. Now, how are we going to describe the intersection? Well, let's go back to my earlier picture. You can use symmetry here a lot. If you want to have Z between two surfaces, right, and use some sort of symmetry, the simplest lower surface is just the xy plane. Okay? So we're going to slice in the xy plane and then just look at everything above the xy plane and then multiply it by some factor. Now, what is this curve here? This is the upper bounding surface for Z. Well, we can get it from here. It's going to be Z is less than root a squared minus x squared. Okay? What about the bounding curve for y? Well, if we look at this curve, this is certainly going to bound y. We can get that from just rearranging this, making y equal to root a squared minus x squared. So let's see if we can clarify our ideas here. So I'm only going to consider the intersection in the first octant. In other words, where x, y, and z are all non-negative. And then I'm going to multiply my answer by 8. So let's call this S1. Okay, now if I draw in this is Z. This is positive x down here. If I draw in both of my curves, okay, so what I've done there is I've just sort of drawn in this bounding curve here. I guess it's just a profile of the surface. And this one comes from, this comes from here. And this one is just here, okay? So in the first octant, this is going to be it. So this is just the following, and this is just the following. Okay. So let's see if we can actually put our volume together. So the total volume of intersection, it's just 8 times the volume of S1. Okay, so let's try to describe this three-dimensional region, S1. Well, Z's going to be between the zero plane and the plane and the surface Z equals root a squared minus x squared. If I draw a vertical line in here, y is going to be between 0 and this curve. Again, it's root a squared minus x squared. And x is going to be between 0 and a. So I've kind of squished that all in there. I hope you can read it okay. And it looks a little bit difficult because we've got all these square root signs, but actually it's not too bad. If I do the inside integral, this is just going to shift in here. Well, let me do it in two steps. If I do the inside integral, I'm just going to get a square root a squared minus x squared. Now, when I integrate that with respect to y, I'm not going to change any of this. I'm just going to get a factor of y there. So when you bring that one in, these two square roots are going to combine, and you're going to get this. So they're going to sort of cancel off. So you get actually something quite simple. Now if you integrate this single integral, you should get something like the following. According to my calcs, it's this. So the final answer then is just the following. So the U stands for cubic units there, whatever their units are. That question, you have no problems with the rest of this course. Okay? You need, this is above what we would expect of you. But this is a challenging problem. And if you can really nail the visualization, even just partly get it, you're doing extremely well. Okay? If you can't do it, well, that's okay. It's beyond, I would say it's beyond this course. But I think it's a really interesting problem. Okay? Now sometimes you don't just have two cylinders intersecting, you have three cylinders intersecting along all the axes. I'm not going to do that one. Questions? Okay. I'm going to do one question on cylindricals. 120. Anyone done it? Anyone done 120? Anyone? Use cylindrical coordinates to find this, the value of this triple integral, where S, the region of integration, is the portion of this, the cylinder, between these two constant planes. Okay, now this is a real simple one. Let's sketch the region, set up the double integral, set up the limits of integration in cylindrical coordinates. Okay, so 120. So this is just to give you a little taste of cylindrical coordinates over the Easter, you know. Okay. So our so let I be the following triple integral. With the region of integration, S, now I'm just going to write this with a less than or equal to sign here. It's still the same region. All right. We want to evaluate. So this doesn't have anything to do with volume necessarily. All we've got is we're given some triple integral. We're given the region of integration. Let's just evaluate the triple integral. Okay? But we don't have the limits of integration. That's what we need to find. Okay, so let's draw a picture and see what's what. So this then is going to be some sort of cylinder wrapped around the z-axis. And we know it's bounded below by the xy plane and above by the constant plane z equals 1. So it's going to be, if that's 1, it's going to be something like this. So this is going to be A, this is going to be A. Now, as the name suggests, cylindrical coordinates are helpful for cylindrical shaped regions. Now, let's just refresh our memory. What are the cylindrical coordinate type of system and their relationship with the Cartesian? Well, cylindricals are a lot like polar coordinates. You've got a length, r, an angle, theta, but you've also got another variable, a z variable, that measures height or depth. Okay? So the variables for cylindricals are r, theta, and z. Okay? So r, theta, and we just add one extra variable, z, to measure height. So let's get the r and theta from the projection. In the xy plane, this is going to be some sort of disk. Centered at the origin with radius a. So to describe this in polars, the description is going to be what? Well, r is between 0 and a, where a is just some constant. To trace this out, theta is going to be between 0 and 2 pi. And what are the surfaces bounding our z? 0, just constants, 0 and 1. That's it. Okay? Now, just like when we looked at polar coordinates for double integrals, we do have to replace this dv with something. Okay? But it's not very difficult. All we replace it with, instead of the dv here, we replace it with r dz dr d theta. Okay? So we replace x with r cos theta, y with r sin theta, and dv with r dz dr d theta. Okay? Or dz r dr d theta. You can do it a number of ways. Okay, I'm just going to do it this way. Okay, so the region, what are the regions of integration? Well, let's write those in. So now we can simplify using cos squared plus sine squared equals 1. Not forgetting to multiply through by my r, so I get something like this. Okay, so I integrate r squared with respect to z, plug in z equals 1 and z equals 0. I'll get, what will I get? I'll get 1. Hang on. No, I'll get r squared. Okay, then integrate r squared with respect to r. It's going to become r cubed on 3. When I plug in a and 0, I'll get down to the following. I'm going to get a cubed on 3. And you can see this has got nothing to do with theta, so all I need to do is multiply by 2 pi.